Today we're going through exercise 2.2 from the Art of Electronics, and in this exercise we are looking at a NPN transistor circuit. We will also analyze another circuit which is on figure 2.92 to get a better understanding of what the question is asking us to do. So first of all, I will go through figure 2.91, which is a transistor power amplifier circuit with negative feedback, and then we will go through figure 2.92 and exercise 2.22, where we need to calculate certain parameters for the circuits, such as the gain, input impedance, output impedance for the closed loop and the open loop circuit. Now, learning to design beautiful circuits, schematics, and PCBs is only part of the journey. If you want to bring your designs to life, you need PCBWay. PCBWay is a high-quality manufacturer of PCBs, and they can assemble the PCBs for you as well. The order process is very simple. You upload your Gerber files and they will give you a quote very quickly. One of the things I really like about PCBWay is their shared projects, which is a community-driven platform where makers can share their electronic projects with other people. I also share my projects here, so if you ever wanted to order one of the PCBs that I've designed on video, you can do that through PCBWay and their website. So again, a huge thank you to PCBWay for sponsoring this video and making this content possible. Now back to the video. So as you can see on the screen now, we are firstly going to look at figure 2.91, which is a transistor power amplifier with negative feedback. The feedback is basically this point over here, which is the output going back into one of the inputs. So for this circuit, what we are going to do is find the open loop gain, the loop gain, the output impedance for the open loop circuit, the output impedance for the closed loop circuit as well. So the first thing we're going to do is look at the input impedance. So let me create a copy of this again. So looking at the input impedance, our signal is coming in from this direction. It's going through this part, and all of this is going to affect the input impedance basically. Now, if we look at a frequency signal that's significantly higher than the impedance that's created by C1, we can basically ignore it, and we can basically say R1 is in parallel with the equivalent circuit that's on this side. So let's draw that out now. So we have our input signal, which is R1. We have some gain from our Q1, so I'm just going to call that A1. We have a intrinsic emitter resistance as part of this circuit here, so let's call that RE1. And going this side, we have the intrinsic emitter resistance from Q2 as well. So let's call that RE2. We have another gain, but that is going to face the other direction. And then we have a 3K3 resistor, which is R5. And we have a 100K resistor, which is R4. Now for the first case, we are basically looking at an open loop case. We are basically disconnecting the feedback from the circuit, which is over here, and we are going to ground R4. So I want to connect that to ground, and again we can ignore C2 because it's going to be relatively low impedance for the frequency signals that we are interested in. Now R1 value is straightforward, it's 100K. RE value, it's going to be equal to Vt over IE1, which in this case is 25 millivolts over 1 milliamp. You have 2 milliamps going in this direction over here. 1 milliamp is going to be coming through this side. The other milliamp is going to be coming through this side. So the current through Q1 emitter is going to be 1 milliamp. So we can say RE1 is equal to 25 ohms, and RE2 is also going to be equal to 25 ohms. So we can simplify this part of the circuit here to just a single resistor. You can see this gain over here is going to effectively amplify the resistance that's here for the input signal. So we can redraw that again, similar to this. So we've basically got rid of our gain on this side, and we have our RE resistors for both Q1 and Q2 represented with this single block. Now the resistance on this side is going to be divided by this gain because obviously it's acting in the opposite direction. So this is going to be two resistors in parallel. Now R4 is significantly higher than R5, so we can ignore that as well. And we can redraw this side of the circuit with a single resistor that's R5 divided by the beta, or the HFE in this case, as it's being called. So what we've done is reduce this circuit to this circuit over here. So we can now calculate the input impedance, but before we do that, let's do the calculations for these resistors over here. So we know RA is 25, so 2 times 25 is 50, and we know HFE is 250, so we can do 50 times 250 is equal to 1250, so that's this resistance here, 12K.5, and our R5 resistor is going to be amplified by the amplification we had over here, and it's going to be divided by the amplification that we had on this side. So we can basically get rid of this HFE, and we are just left with R5. Obviously, we've said R4 is significantly larger than R5, so we're ignoring it. So the input impedance, Zin, becomes 100K in parallel with 12K5 resistor plus the 3K3 resistor that's over here. So 12,500 plus 3,300 is equal to 15,800. So Zin is equal to 100K in parallel with 15K8. So if we do that calculation, it's basically 1 divided by 1 over 100 plus 1 over 15.8, which is equal to 13,600 kiloohms. Now I think the book ignores the 100K resistor that's over here. And if we ignore that, we get 15K8, which is very similar to the value that the book has. Now the book completely ignores the R4 resistor as well, which is a 100 kilo ohm resistor as well. So maybe we should ignore both, or we can account for both. Now if we did account for both, then we'd get a value that's closer to 13,644, and that's because the 3K3 resistor, if we add in the 100K resistor over here, would give us maybe 3K2, something like that. So I think we can safely ignore the 200K resistors and we'll get a close value, but we wouldn't get the value that the book has. Next, we want to look at the output impedance. Now you can see from the circuit Q4 and Q5, which is these two power transistors over here, are driven by R6. Now if the Q4 and Q5 beta or HFE value was 100, we can basically say that the output impedance for this circuit in open loop, we basically disconnected this connection over here. We can say that Zout is equal to 1K5, which is this resistor, R6, divided by the beta value, just because of the gain looking out from here, which is basically beta from these transistors. Now, one of the things we kind of neglected is the R7 and R8 value. So if we bring those back in, then our output impedance is basically 20 ohms. So that's going to be 15 plus 20. Another thing that we've ignored is the intrinsic emitter resistance of Q5 and Q4. But if you look at that value, so let's say RE is equal to VT divided by IE. So that's 25 milli on top of 60 milli. Now the 2 millis cancel and you end up with 25 divided by 60, which is approximately 0.4. So obviously 0.4 compared to 20 is insignificant, so we can ignore it. So this is the output impedance for the circuit shown on figure 2.91 for open loop. Next, I'm going to look at the gain. Now this circuit, if I was to just go into a bit more detail, you basically have a differential pair here, and the load on that differential pair is this resistor over here. Now the output from this differential pair is taken from here, which is amplified by Q3, and then it's fed to the output driver circuit, which is Q4 and Q5. The diodes are basically biasing Q4 and Q5, so they remain just slightly switched on, and basically that wastes maybe 1 watt of power in standby. Now for the gain, we basically need to go through that chain and calculate what our open loop gain is going to be. So first of all, we have this transistor over here, with its collector resistance R2 in parallel with some equivalent resistance from this part of the circuit here, and RC and RE. So RC is this resistor here, and the emitter resistance is going to be the two resistors that are over here. So first of all, let's look at R2 and the equivalent resistance in parallel, which is a result of Q3's base. So we know the current through Q3 is 10 milliamps, just because that's given over here. So that current has to flow this direction. So Q3 RE is equal to 25 milli divided by 10 milli. The 2 millis cancel again, and you end up with a RE resistance of 2.5 ohms, which is given in the circuit over here as well. Now RE is basically amplified by the gain of Q3. So the resistance appearing for now RE is amplified by Q3's gain as well. So the resistance that appears in parallel with R2 is Q3 RE times the beta of Q3. So that's basically 250 ohms if we assume beta is 100. And that's also given in the circuit over here. So our first RC is equal to 620 ohms in parallel with 250 ohms. Now if you look at the RE value, is basically the emitter resistance of Q1 and Q2, and we already know that they are 25 and 25, so that's going to be 50 ohms. So we can calculate gain as RC over RE, which is equal to 178. So 178 on top, and on the bottom we have 50, which is equal to 3.56, and now the book says 3.5, so I think that's close enough. Next, we want to look at the gain of Q3. So Q3 basically has a RE resistance of 2.5 and an RC resistance of 1500. So let's just put that in. Now 1500 divided by 2.5 is equal to 600. So now we know the gain of this section, and we know the gain of this section over here, and those gains are in series. So if we multiply those two numbers together, the overall gain is equal to 3.5 times 600, which gives us a gain of 2100. So you can see that matches up with the answer that the book has as well. Now if we look at a closed loop scenario where this feedback is not removed from the circuit, our output impedance is reduced by 1 over the loop gain. And the loop gain is basically equal to the feedback factor times the overall gain. So the feedback factor in this circuit is basically determined by this section over here. So you can see that this is a potential divider. So if we ignore C2 for high frequency signals, we basically get 100k on the top resistor and 3.3k on the bottom resistor. So if I draw that out again, the signal that's going to be coming out over here is going to be equal to wherever this signal is. So let's call that V out, and let's call that VFB. VFB is equal to V out R5 over R5 plus R4. Now our R5 value is 3300. Our R4 is 100,000. So let's do that calculation. So you basically get 0.03, which is our feedback factor. Now if we multiply our overall gain, which is 2100, with the feedback factor, which is 0.03, we get a feedback factor of 67.2. Now in the book, they've used a value of 70, so I'm just going to assume that's close enough. Now if we look at the output impedance, it basically gets reduced by the loop gain, which is this number over here. So our output impedance is going to be equal to, so Z out CL is equal to Z out OL times divide by 1 plus 70. Now our Z out was equal to roughly 20 ohms. If we divide that by 71, we get a output impedance of 0.28 ohms. So that's roughly 0.3 ohms, which matches up with what the book has. The last thing we're going to look at for this circuit is the gain for the closed loop circuit. Now, if you remember the equation, which we have derived in the past, GCL is equal to the open loop gain 1 plus the open loop gain times the feedback factor, which in our case is this number over here. So the closed loop gain is equal to 30.8, which is what's given in the book. I mean, the book uses 70. If I use 70, then I get a slightly smaller number, but it is what it is. So if you use the number that we actually calculate, we get a number for gain that's closer to what the book has. Now we basically analyzed this circuit. We need to do a very similar thing for the circuit that's given in the question. For this exercise, we need to find the open loop gain Z out, which is the output impedance for open loop, the closed loop output impedance, and the closed loop gain. So G open is given as 200, the loop gain is given as 20, the output impedance is given as 10K, and the closed loop output impedance is given as 500, and the closed loop gain is given as 9.5. So what we're going to do first is basically look at this circuit in a bit more detail. So you can see we have a potential divider over here, which is driving this transistor Q1. Now the circuit itself gives us the driving voltage over here, which is 2.6. You're going to have roughly 0.6 volt drop over here, which gives you 2 volts at the emitter junction of this transistor. This is the collector, this is the emitter, and obviously this is the base. This is our collector resistor, which is 620, and the gain of Q1 is going to be RC, which is R3, over the RE resistor, which is R4. Now the RE resistor also includes this resistor over here, which is going to be 25 ohms roughly, but we can ignore that. The output for the first part of the circuit is taken from the collector over here, and this PNP transistor Q2 is basically taking that output. Then we have some feedback through R5 back into the circuit. For the open loop analysis, what we're going to do is cut this point over here. So we are basically removing the feedback, and then we can look at the open loop gain. So the first part is going to be gain of Q1 is equal to RC over RE. Now RC is a parallel combination similar to what we saw for the first circuit, with R3 in parallel with the equivalent Q2 resistance. So I'm just going to write that as Q2 EQ. Q2 equivalent is basically equal to RE plus RE, which is the intrinsic resistor, and this is the physical emitter resistor that's connected to the emitter. As you can see on the circuit, there's nothing connected over here, so RE is 0. So Q2 equivalent is going to be RE. However, we need to consider the gain. So if we calculate RE for Q2, that's basically RE is equal to VT over IE, which is 25 milli divided by 1 milliamp, which is the current that's flowing in this direction over here through this transistor, which gives us an RE resistance of 25 ohms. The equivalent resistance is going to be amplified by the gain of the transistor Q2. Now, if we assume Q2 beta is equal to 100, then that gives us a Q2 equivalent resistance of 25 times 100, which is 2500 ohms. So RC is equal to 620, which is this resistor over here, in parallel with the equivalent resistor that we just calculated from this base over here. So 2500. That gives us an RC value of 497 ohms. If we calculate the gain for the first stage, then that is 497 divided by 1K resistor, which is basically this R4 resistor over here. And that gives us a gain of 0.497, or roughly 0.5. So the gain of the first stage is 0.5. Then we can calculate the gain of the second stage, which is basically Q2. So Q2 gain, again, same equation, is equal to RC over RE. We have already calculated that RE is 25. So our RC resistor in this circuit is basically this 10 kilo ohm resistor over here, basically R5. So we have 10,000 kilo ohms divided by 25 ohms, which gives us a Q2 gain of 400. Now the overall gain for the open loop is going to be 0.5 times 400, which is basically 200. And if we refer back to the question, we have found this. Next, we need to find the loop gain, which is basically equal to the feedback factor times the open loop gain. So we have already found the open loop gain over here, and the feedback factor for this circuit is basically 10 kilo ohms on top of a 1 kilo ohm resistor over here. So very similar to the calculation that we did for this part over here. We basically have another potential divider that's reducing the amount of feedback from the output that's going back into the circuit from here. So 10 over 1, that gives us a feedback factor of 0.1. Our open loop gain is 200, so the loop gain is going to be 0.1 times 200, which is equal to 20. Now going back to the question, we have basically found this. The output impedance for this circuit is very simple. So you can see we have basically just this resistor over here that's before the output signal. So our output impedance for the open loop when this is disconnected is basically this 10 kilo ohm resistor over here. Now when this is disconnected, this would most likely be grounded. So that's 10 kilo ohms that's coming straight from R5. Next, we can calculate the closed loop output impedance, which is basically reduced by 1 plus the loop gain. So we have our output impedance for open loop was equal to 10,000 ohms. Our loop gain is 20. Our closed loop output impedance is going to be the open loop output impedance divided by 1 plus the loop gain. Now the loop gain is equal to 21. And our open loop output impedance was 10K. So we can write this as 10,000 divided by 21, which is equal to 476. So you can see we've got a output impedance of 500. Now, if you go back to the question, that's another tick because that's what the book is asking us to derive. And the last thing we need to do is get the closed loop gain, and the author has given us a value of 9.5. Now the equation for the closed loop gain is very simple. So GCL is equal to the open loop gain 1 plus the open loop gain times the feedback factor. And if we plug in those numbers, which is basically 200, 1 plus 200 times 0.1, that is equal to 9.524. So that is the closed loop gain for this circuit that we are just looking at. Now just referencing back to the question, we've basically got 9.5 over here. So we've got to the right solution that we need to approximately, because obviously that's only to one decimal place. And we have 9.524, which is approximately 9.5. And that solves exercise 2.22. So hopefully you enjoyed the kind of longer explanation for this circuit, and I've included a circuit just before this question to try and understand this question a little bit more. I think it was necessary for this question. Let me know if you have any feedback. Thank you for watching. Bye for now.